All right, we're live. Go, Tibby.
Hello everyone from Sensorica Lab. This is a live work party like the ones we usually do to advance the PV project. Mainly a coordination for hardware. We need to solve some problems with the 3D designs of micromanipulators. So this is mechanics, a little bit of electronics there too. Tammy, it would be nice if you can pick up from these work problems that we need to solve and then think about the outreach strategy to get more people to participate if the skills are not available within the network right now. How do you feel about that?
Great. Yeah, maybe you can start off the top with talking about the challenges that we're facing with the micromanipulators.
Yeah, so I do have the 3D model here, so we can go through it. And I think idea for this work party is to identify the challenges as we go along, right? And see where we could use some new skills, some new people. We haven't identified all the problems. Okay, so we go through it one by one, right?
No, of course.
Perfect.
How it fits. Were you successful to install the camera? Or?
I need you to invite me to the Hangout because there's...
Okay, check the email for Sensorica, 2 birds in 1 stone, and you have the...
okay, there we go. Link to Hangout. Yeah. This one here?
Yeah. Okay. So Jim is connecting another camera just to give you a context on the table for the physical parts. And what you see on the screen now, it's funny. You see, I put the 3D model here, so...
I just chatted Jim the link to the Hangout.
Okay, I got it. Oh, there we go. Okay.
Beautiful.
Okay,
Jim, you gotta mute.
Yeah, okay, let me in here. What?
Oh, for the...
Okay, mute screen.
Beautiful.
This is not the
But this thing was a clamp. So.
Okay.
There we go. Where's that scanner? Yeah, Whatever happened to it? I don't know.
So your camera's frozen, Jim. And Tibby's has just gone to the Windows screen.
Yeah, my computer just shut off.
Yeah.
Okay.
Yay!
Okay, well, technical challenges. There they are.
No, into this one. Or you want to be here to use it, eh?
Yeah, since we're live, I don't want to disturb this.
Okay.
But you can get the other computer, Daniel.
Hi, Tammy.
Hey, how's it going?
We're just pretending like we're not here.
Great. Nice to see you. All right, so there is the unit.
Is Daniel here?
No, go ahead. Go ahead. You can take it out of there.
It's gonna crash again.
Why?
I don't know.
Too much stuff?
The webcam thing.
Oh yeah?
Yeah.
You always have this thing, or?
It's always happening when I'm on Hangouts.
Did you have to install a driver for this? Or?
No.
No?
No.
I can try it here if you want.
Live troubleshooting.
Yeah.
Okay, so this is in SketchUp?
Yeah, so since we're talking about the mechanical problems, we're going to look at it now. We have
I
two
believe I just
models
cleaned up
that
my
have
desktop like
some
3 days ago.
mechanical problems.
Yeah.
I didn't know.
I want to start with the micromanipulator, or should we start? Yeah, we can start with the micromanipulator.
I prefer having 2 computers to work on than having 30 tabs open.
Oh yeah, yeah, yeah. But like that's what I used to do is like use 2 computers at once. With my Linux anonymous machine and my personal machine.
TV.
Okay, so this is the body of the micromanipulator.
Yeah, the first box of the micromanipulator. I want to talk about the railing system.
Yep.
Let's see how it goes together. So,
Danielle, could you come a bit closer to the mic?
oh, sorry. Yeah, I can do that. Okay, so you see this part here. These sides here
Yes.
are this big groove over here
Yep.
is fitting inside this box rail. Okay, but it's not a good sliding system because we have too much movement, and depending on how you print it, what material you use, what nozzle you have on the 3D printer, depending on many things, okay, you're gonna have to change your instructions.
Jim has to mute. Yeah, good.
To get that thing right, okay?
And that's so that it doesn't have play, right?
Yeah. So it's not a good system. We need to change that with something else. And I don't have ideas. I wonder if people can jump in with flash ideas, you know, to see how we can change the railing system. Because you see, it's sliding on that rail in the middle,
Can you
and on the
point to the
top,
rail?
and it's sliding on the top here, on this top surface, this side and this side.
So could you do some lift grooving? Some upward grooving? Because on top of that is the slider, right?
Okay, Kami, I just created a document here, and I shared the link in the chat box. So let's take notes in this document as we go through the model. And you can create yourself a section in there for outreach if you want, or skills needed type of thing, right?
Okay.
And okay, so let's structure this thing. Let's structure this approach for the mechanical problems. So I will have the camera and I show you. So this is the guys. Let's look at it here. So this is the micromanipulator basically. It sits like that. Problems is this, the fact that it's moving. So Daniel is talking about the rails. Daniel.
Inside, yeah, but because we don't see the rail inside now.
Okay, so show me the rails inside.
Well, I showed it.
Okay, so now it's on the screen. So this part here, it's moving. It's making this, the groove that you see on the 3D model. It's making this part moving, and the problem is that the way it sits on it, it moves. So now Frederick had some ideas. So he said it's all about the size of that groove with respect to the base, with respect to the whole piece. Okay, essentially what he's saying is that
There's not enough surface area.
yeah. So essentially what he's saying is that if you have a large base for a small piece, if the piece is very stable. If you have a large piece sitting on a very small base, it's going to
It's gonna
wobble,
wobble. Yeah.
right?
Yeah.
So making a larger base, it'll reduce the
Okay.
it'll reduce the
Can we open it up and see the inside and see what's going on?
here the
Or you can show it in the model?
well, Daniel can bring other pieces. Daniel, can you bring other pieces of one that is not?
Yeah. The challenge here is to make it as compact as possible.
Yeah, of course. That's the challenge. Um, and the other axes work good, Daniel. They look pretty good. The other ones, eh?
Yeah.
So it's just that one we're having trouble
The
with.
Z-axis has the same railing system, but it doesn't move that much. Very little.
Where's the Z-axis is?
Okay,
Where?
these are failed parts.
This is the okay. Explain to me the axes here.
First one is x-axis.
And is X, tip, tilt, or rotation?
Then the second axis is a rotation axis. Okay, it's this one. So the center of rotation is here. And this,
Can I see that, Daniel?
Yeah.
Okay. So yeah, the first axis is this one.
Yeah.
It makes it travel like this.
Okay.
Then the second axis of rotation is a rotation, is not a linear axis.
Okay.
So by turning this,
You swivel it.
it moves this little thing. Okay, you can see it now.
It's a sort of
Rotation. So it's got 9 degrees of rotation in each direction.
9.
Okay.
So that makes 18 degrees of rotation. Okay. It rotates this way around
Pivots.
this
Okay.
axis.
Okay.
Yeah.
And then the third axis is a linear axis. Is the Z. Okay, which is
Okay. So it's up down.
up and down. Yeah.
Okay. So which is the one we're having problem with now? It's the.
It's the Z because
Yeah.
this one is very tight. I don't know. It came out very good with the tolerances and everything.
So you think that if we it's a hit or miss when you're printing the parts, basically, or we could adjust the actual sizes and maybe make it better.
But one rail is not enough. I'm gonna try to squeeze
that's
2
what it is,
rails
eh?
in there.
No, it won't be
And
enough.
and the farther they are apart, that's right. The farther they are apart, the more stable it's gonna be. But the challenge here is to have a very small footstep for every because we have 3 micro manipulators like this on a very
Yeah.
small surface.
Yeah.
So this is the big challenge is to.
Well, let me ask you something. If we increase, because I mean the base is this wide, right?
Mhm.
That's the size.
No. The base on which this one sits is the rail. Yeah,
I know, but we have
the base. Yes.
the base is this.
Mhm.
So why don't you extend the base all the way?
Because you have to maybe they're gonna use screws to fix the base to the.
No, they can't because they have to physically manipulate it first. Then they have to move in.
Yeah, he
Yeah,
designed it
controls.
for other uses. Yeah, it's a universal. It's a universal usage. So if you don't want to use magnets and you want to really have it.
Oh, you
on a
designed it for
breadboard.
more. Okay.
Yeah,
But for the scope of this project, we could. Well, I understand what you're saying.
yeah, and
You
plus
wanna make
the
that
magnets, you have to insert them and they need some space, so they will take.
Yeah, but I mean, you could have a hole here and glue the magnets.
Yeah, but it would take would have the same
Or have a cap or.
Yeah.
I understand what you're saying.
So here's my input. Okay, so
Yeah.
okay, so if we look at this, let's step back. Okay,
Yeah.
let's step back. So the idea here was to have a micro manipulator that is 3D printed and with a minimum amount of pieces, so it slides plastic on plastic. So there is some rails that are inside here on which this part slides. Right. Now, another idea is to
Insert a rod.
insert 1 or 2 rods. I mean, 1 is not enough because if you
No,
just
it's-
have something on a rod, you have a rotation.
Mhm.
If you insert 2, then there's no more rotation,
Mhm.
and you can align them. And now rods like these are very available, really cheap. You can get them very straight and even thinner than that, and have it move on 2 rods. So now you have something that slides
Yeah.
on metal rods like this. That can be pretty good You know what I'm saying? With no
No play.
with no play, and you still use a screw, the same screws, okay, to put it up and down. So that would be adding rails to the system instead of having plastic on plastic and playing with tolerance and stuff like that.
Can I ask you a question? Instead of having rails, can't we have screws? Can't we use screws? We already have screws in the system. Can't the screws be incorporated in the design to act as the rails? Instead of
It's
having
just
a rod?
the screws, they always have the little
Oh,
backlash or
Okay.
So essentially, it's adding another
screws and nuts. They are always there is already.
Well, because here I see you have, what's this screw for here? Is that part of this? Oh, it is.
Yeah,
It's part of
yeah.
this. Okay, okay.
It's to activate. Oh no, you
That's
you
to
reach
lock it into place.
No, you reach the end.
I reached the stop. Okay.
So this is what it's normally.
I didn't put glue here.
This is what you normally find in micromanipulators, right? So you have a part here in the middle
Yeah.
that slides
Mhm.
on a rail,
Yeah, with rods and.
Okay. and then you have the actuator, which is your screw that makes it move either way, right?
Okay.
Now, the idea here is that these rails are adjustable by set screws.
Mhm.
Okay, so that's another feature that we don't have there, which is you have the rails which are rigid mechanical devices
Mhm.
that guide the motion. And then you have an element of flexibility here that allows you to adjust
The amount of
the
pressure.
pressure on the rails so that there is no
There's no give.
play here. You know what I'm saying?
Yeah.
And then, yeah. So that's another thing that we can add. So we can add a rod like that, two rods like that, with some set screws to make them parallel. Okay, to have it go in a straight direction. So rails. Okay, that's another concept that we can use. There is a rail here, plastic on plastic, and I don't know
Yeah.
how good that is.
But
And then-
if we want to try to keep it simpler, can we add a second? Can we add two rails? Second
Yeah,
rail?
yeah. The top of the rails is pretty soft, and there is not so much friction between the plastic and plastic parts. I don't think there will be any wear.
Well, it's not about rotation; it's about translation. So we're talking about-
if we put two ball bearings, like in two grooves.
Mhm. Oh, that's what these use.
Yeah, this is
They
exactly
use
what this uses.
linear ball bearings
See,
Yeah.
there's a rail, and they have ball bearings inside here.
that you can adjust so that the pressure is equal and is parallel.
Yeah.
So would the rods impact the, sorry, it's the Z that we're talking about? The
No, it's the x-axis. The
X.
z-axis also
Right.
it's the same principle, and but it's much smaller.
And they're just direct. They're not swiveling. So and those are both tight. Those
Yeah.
are fine. So it's
Well,
the
this has the same problem. I mean, the z-axis, by chance, it is actually, Danielle, it's because it was at the maximum. But if you bring it down,
Mm-hmm. Yeah.
you see, it still has a play.
Mm-hmm.
The problem here is if we, okay, let me go to the, let me go here. So, can you put this on the screen? Okay, Daniel, how do I just select this card?
Double click on it.
Okay.
And double click again.
Okay, here's the problem. So this is the groove. Here is the groove. Do you see me over there? Okay. Whoa. Okay.
Yes.
So this is the groove on which the thing slides.
Yep.
You see, Jim?
Yeah, I'm looking.
Okay. So it slides. This is what ensures the linear motion. And then the wobbling left and right that we see, it comes from these walls, this and this, because this sits into a square. This sits into a square box.
Guys, isn't like an inverted V like that? Is it inherent that it's going to wobble?
Or maybe it might bind.
So wait a second. So in order for this to go straight,
Yeah.
okay, it has one to be supported down here
Uh-huh.
to slide on something,
Yeah.
and to be supported on this wall, not to go this way, and be supported on this wall, not to go
Yeah.
left.
Yeah.
Okay.
Yeah.
Well, on top of the wall. Yeah.
Now here you have a tolerance problem because you have a square box. You fit this into a square box. So if you have a little room here, okay, just sitting on this rail, it's going to wobble within this little space that you have.
But let me ask you, if the walls of the groove, instead of being at an angle, if they were perpendicular, wouldn't that
You mean this groove here to be square instead of being a V?
Yeah.
Well, that's even worse.
Is it?
Yes, because
Okay,
now you're trying to fit a square into. Every time you have to fit a square into a square,
Yeah.
Yeah.
you have tolerance problems with the 3D printer because you have to fit them within microns. Okay, and 3D printing doesn't have that tolerance.
Yeah, but I mean, there's always sanding.
So
Well,
what if
Or how about a parabola?
I've got something?
Or so you don't get the binding as you would in the V-type structure on the side.
Yeah, well, the idea here is to have something that just slides in and then it stops because it's a V groove, and as soon as it stops, it's there.
Mhm.
But now, if you do that on top, okay, if you do that on the sides, you also have to be like spot on. Now, either you put some set screws with some bearings, and you adjust that distance by the set screw and the bearings, and now you're fine. But this design doesn't have this flexibility, so you have to fit into that box precisely in order to have it not wobble, which
So
is
what if
too much from a 3D printer. Yes?
so what if there was more grooves in that groove that's there, like a groove on each side to hold it
Two
more
grooves?
stable?
Yeah, that could be a good idea.
On the top walls, on the top of the walls, yeah.
Yep,
And,
just
and
to
also
give that more stability.
in the other part too. Can you show the other part? Double click outside, and double click on the top on the part that goes
Yeah,
on
that
top.
could be a good idea. Share the load and
The bottom one.
This?
Double click on it.
This one?
The bottom one. Yeah. You see, it's got the V groove on the bottom, but
Yep.
there on the top where it touches those vertical walls, it's square. So V groove there, V groove on the walls, and maybe that may fix it.
Yeah, that would just give it more sort of internal stability.
Well, what is it? I don't understand. So instead of having one V groove here, you have one here and one here, like two? Is that what you're talking about, Tommy? On the base, having two V grooves?
No, on the inside of the existing V groove.
Oh, just make like another V inside, you mean?
Like a divot on either side to be able to give it a bit more stability so that it's not just sitting in there. It's being guided by mini guides within the track.
I can squeeze in two V grooves on the bottom.
Tommy, can you draw it on the document? And I'll bring the document up. Can you draw it on the document what you want to see?
Can you
Use
paste
the
it there?
insert drawing.
In the 3D model, it looks big, but when you actually print it, it's very small. So I don't have much space in there. I can squeeze in two slides and make V grooves on the top. Because I want to avoid using metal rods and,
just avoid
and the adjustment screws.
yeah.
But it's true that it would be perfect.
Well, I don't think we have any choice. Yeah.
But I've seen
Yeah, the only problem is
Other
you're
3D
increasing
printed-
the surface area and you'll increase friction. But
yeah.
there's always a compensation about something, eh?
yeah.
But it should make it more stable.
Well, the idea of the V grooves is that you put one here in the corner and the other one here, and you still have the screw in the middle to drive it, right? And friction, I mean, you just turn the screw to drive it. It's
Oh,
not-
and you know what, guys? These holes for the long screw. Okay, are you looking at the 3D model screen?
Yeah.
Okay, so these holes for the long screw, they were designed too big. Okay, because I thought the tolerance would be that, but in fact I had to change their diameter for better tolerance. after I print them, I measure them, and I realized that, oops, sorry, where is that?
Yeah, you were off.
People. Uh-huh.
So wouldn't that help guide it as well? That center screw?
So you see, here's where we change the
No.
tolerance, the diameter of the.
Usually the screw is not used as a
Okay.
So I have drawn what I mean in the document.
Did you close it? Let me see.
It's in the document.
Tommy, you want to share your screen so I can jump to it?
Oh yeah,
I don't see it, Tommy.
it's at the top.
Wait a second. Oh.
I mean, it is a rough drawing. But yeah, there. Just, and obviously not quite that pointy. It kind of looks like horns. But just another guide on the inside. I know it is quite small, Daniel, but having those grooves might allow it to be more stable from within that part of the unit.
Or maybe see some ball bearings in there. Make the groove circular. But see, so prevent the binding, eh? Because when you have a V groove, there's always a chance of binding.
Well, I thought the binding was trying to prevent it. We're trying to stabilize it.
Yeah, you're going to increase the friction to exponential rates. Okay.
Yeah. Well, Tommy, the problem with this is the assembly. Because you would have to slide that in somehow.
Yeah, it's true.
It would have to be a snug fit. But what it is that we're talking about is not having any play. So.
You have an opening on one side on the design to slide it in.
So here's how it looks. If I go, can you put me there? Okay. So here's how the part looks. Okay. This is the box in which the other thing slides. So this is the groove. Okay. So it's sitting on this groove and then it's wobbling inside this box. That's the problem.
Okay. No, it wouldn't work.
The assembly is just dropping something in the box and then putting the set screw in it. The way we would assemble, you see? Now you can see it better.
So your idea, Tibby, would be to make 4 holes and insert 2 rods, slide 2 little rods in there that fit inside. So you drop the part in, and then you slide the 2 rods. And how do you have to glue the rods?
So you would glue, yes, exactly. So okay, so here.
Yeah, it's 4 holes just adjacent to the big to the hole where the screw goes in.
Yeah. So one rod can go in here.
One rod could go there. The other one could go on the other side.
The other rod can go on the other side.
Okay.
And then they both fit into 2 holes here.
But you don't need to screw them on both sides. To glue them on, you just glue them on one side, right?
Well, let's say you have a through hole here and another through hole there. So as you put it in, you push it towards the end, and then you put a cap.
Yeah.
To fix it in place. You can put some glue to fix it in place.
Yeah.
And now you have 2 fixed metal rods.
Yeah, there's no way that thing is budging, right?
And there's
yeah.
exactly. So then
and you reduce friction.
Do you keep the V
then you have this part here. You see.
Okay.
Now you have this part here. So one rod goes inside here, and the other one goes inside here. You just as you drop this part into that box, you slide the rods into it.
Yeah.
And this becomes rails.
Okay,
they become rails. There's
easy,
no way that thing can move.
How easy it is to find these rods? From where do you get them?
You get it from McMaster-Carr easily. You can find them into CD-ROM. I mean, we can just cannibalize some CD-ROMs.
Like 10, 18 stainless steel would be perfect. The highly polished surface, reduce friction.
These are readily available. You can see them in the box here. Now we scanned.
So we want something that's very easily available, eh?
Yeah.
But,
No, there's ones that hold printers. You find stuff like this. And
Yeah.
You just cut it from them.
Yeah.
Here, so this comes from. This is already cannibalized.
What are you looking at, Jim?
I'm looking to see if there's any rods in here that we might be able to use. Yeah, so this this has that exactly that. It's got two rods right over here.
These are precision rails.
Yeah, the
So-
precision rails. Let me see the.
So here's how this is done.
There's no. There's a spring here.
Yeah. So this is how it's done here. If you can take a look. So you see, there's a set screw here, and a set screw here, a set screw here, and a set screw. That's to make it parallel. And there's an adjustment here. So these things make them parallel because if they're not parallel, if they're like
yeah,
this,
it's gonna bind.
you're gonna have a rotation, right?
It's gonna bind.
And this one is to adjust the parallelism this way.
Mhm.
So it's
Yeah.
this way and this way. And they have some set screws to adjust it. So we can think about that in the model too. You know?
Yeah, and they
Anyway,
have,
so this is the rail
look,
concept.
they have
Okay?
they have brass inserts. So that acts like the bearing, right? Like the friction bearing.
Yes, yes, yes.
So it's a softer metal. Is that it?
But that makes it complex, and I wanna.
Yeah, you want to avoid complexity, of course. Well, I mean, it doesn't hurt to try two rails, right? What do you think?
So here's how it sits. You see, so this is the part in the middle that we were showing on the screen with the groove. Okay?
Yeah.
And this one is the box that is not finished with the rail. No, actually, no, Daniel? Yeah, that's it. Okay, I have a bigger one here. So this is it. Okay. So basically, this one slides on this groove here in the bottom.
Another motor.
Here. Okay. So there's a groove here that goes on top of this rail.
Yep.
Here. Okay. And this is supposed to slide like that. The problem is this wobbling. Because this, if you continue printing, this box is going to grow, and then it's going to be stopped on the walls. Okay. But
So can you show me where the rods would go?
the rods would go here and here, like opposite sides.
I can't see where you've got it placed because it's under the boxes of people. Yeah.
Okay, so let me get something to point. Okay.
More central in the picture, if you don't mind.
Yeah. So we scrap this this groove. This groove here is scrapped, right? Not need to use it. And now you would make a hole here and one here, or you can make a hole here and here if you want. Yeah, it's better to squeeze them. Okay. So you need smaller rods because these ones are too big. Let's say we use, or make it bigger. We can just make it. I think it's, size is not a problem here. And then it slides on two rods.
Okay.
Actually, that's a good way to see it, right? And then here. It doesn't matter how they are, the rods positioned, right?
No, as long as they're parallel and they.
That's a concept. So
And
we
can
try-
they go? Can they go more on the outside as guides, or do they have to be embedded in it?
Well, the rod and this part have to be one system, and this slides on the rod. Now they can be outside if you want, or inside or whatever, as long as this goes into some holes that are mechanically attached to this, and this slides on the rod.
Okay.
It doesn't matter where you put them, right?
Because I just think there might not be enough material there to really be able to put rods inside. They
Also-
might be better.
Yeah, there's not enough meat there. Maybe half holes, half like a groove.
Yeah, half in, half out.
Well, if you do that, then you might again have the problem of, I don't know,
Tolerance.
yeah.
Yeah. You're always gonna have a problem with tolerance. It's just that now you have a nice rod, polished and very linear. And then you have to adjust its parallelism. I think that the printer prints the rails parallel anyway. There's the movement X, Y, Z, CNC.
And how
Okay.
how would the how would those rods impact the other angles, the Y and the Z? Would there be any impact?
No, there will not be an impact because this part is separated from the other ones. They're just modules. They're separated modules.
Okay.
Where is the whole piece, guys? Where is the whole piece? The here. Yeah. So these are modules essentially. Okay. So what happens inside this little box here doesn't affect what's on top.
Got it.
Okay. So we can modify this without
Can you
any.
show me where the guides would go on the whole unit?
Well, the big Xbox.
They would go here and here.
Okay. So as being metal rods, they'd need to be a specific length so that they work well with it. Are there parts that are available that are a specific length for rods? Because they're metal, it's something that you'll want to have kind of machined properly, I would suppose.
I don't know. These are just off-the-shelf rods used in the industry. There's no problem with this. They're very available. You can even find them in old computers. So if you don't want to buy them.
And it would be a fixed length? What is the length?
There's standards of these things, and if it's longer, you just got it. That's not a problem, Tommy.
All right.
These are standard PCs manufactured in China by millions, so we have economy of scale there.
For our benefit, before you wrap it up, can you go back to the big picture and talk about what the whole thing is for?
Yeah.
Yes. Okay, so what do you see there in terms of outreach? So I think we need to structure this to the outside, see these are the problems, and propose some solutions and try to crowdsource it, right? So we would need some mechanical.
So I was wondering if what was wanted was kind of an overview as to the PV characterization project and how it came to Sensorica and where it's at. Is that more what was being asked as far as what we're showing today?
I just want to wrap it up. I just want to wrap this up because we're also working, right?
Yeah.
Okay. So just if you can take these notes, right? And now just to go to the other thing, in terms of outreach for electronics, Jit, can you?
Yeah, so, okay, let's get into that. For startup, they're saying we don't have all the equipment in the lab yet, fully custom system. We're missing the IMU, which is the feedback system.
Yeah.
This is a scratch-built triple-phase inverter, okay? So basically, these are like the H bridges that drive stepper motors. Only it's half a bridge. So the bottom MOSFETs are all set on low, and the top ones are sent an individual sine wave, 180 degrees out of phase, 120 degrees out of phase. So basically, what that does is the Arduino looks up on a table, PWMs the right value to each phase of the motor, and slowly turns it. So if you want to get a look at the precision and the control over the speed that I have, I'll just switch the camera over here.
Yeah. It might. Yeah, I didn't want to do that because
Why?
it might interfere with the.
Well, you just have to go here and select this one.
Yeah, you see, sometimes it's.
Hold on, it's good. It should be right. Oh, no, it's ready. Here.
Yeah, and don't shut this off because the live video will run on.
Okay, so we can get that to work.
Installation of hardware compressor.
Okay, it's solid.
So what channels have you guys used to be able to engage with people who are mechanical engineers? Where do you usually put out the word for that? So you broadly do it on Facebook, that sort of thing?
Yeah, so can be anybody, anywhere. Use the Sensorica channel, and what we have created a document with a list of communities that are essentially Fab Labs and open hardware communities that we can go back and send some calls for collaboration. So there's a document with that that I can share with you.
I've gone a little beyond that. I've gone on specific forums that deal with other communities that use similar technology, and that's where I basically learned. Up until 2 years ago, this was unheard of, using brushless DC motors.
Yeah, yeah.
It's been mostly the technology has been innovated mostly by the drone community that uses cameras and attaches cameras to drones with gimbals. And but I've been following. We actually did get one programmer that was involved that I found on with that forum. That's Thomas from.
Was that from the man from Belgium?
Yes, yes. Unfortunately, he's not with us today. He's at Proof of Concept 21. That's the big event in France there, the open source sustainable gathering that's happening in France right now in some castle.
Awesome.
Yeah, and he's there for a couple of days, so he should be back on the project on Monday.
Good.
And he's one of the strong ones with the software development. Too.
So for hardware, I'm going to take some notes, Jim.
Yes.
What are the needs and what kind of people we need, and then just for the people that are going to be watching the video after, we give a short overview, right, of the whole thing. I mean, if you can explain what it does and to put them in the general context.
Yeah, sure. Just trying to get it running because it was running 2 seconds ago.
Would you guys say that you'd like more participation with the mechanical design, or is it mainly the software that?
Well, we have the people for the software. We just need them all on board.
Yeah.
They're all there, but they're just not all available. So yeah, we probably do need some outreach for that. As far as the electronics is concerned, we just need to get the rest of the parts to the lab. So we're missing the IMU, and I mean this is doing a job for now. It's basically a component-built triple phase inverter. That's all going to be replaced by one little chip. So as you can see, the motor right now.
So you're going to explain. Okay, so take us through the whole system.
Maybe you can start, Tibi, by just talking about the purpose of the project, just so that we don't get lost in the details and the acronyms, but start off with what is the PV characterization project?
Yeah, sure.
Just put this out for a wider angle here. Okay, so this is the context of the table. There we go. Say that for Jim. Is this good enough, or? All right.
Okay.
Take it from here, buddy.
All right. So this project, given to us by Joshua Pierce of Queen's University, is essentially a scientific instrument. It's a platform for that. It's essentially a gimbal that has 2 axes of rotations. So its function in the lab is his function for this is to be the test bed for characterizing photovoltaic cells. So specific requirements were given for us to make this an open source device, to socialize the project, to create a community behind it. And we spent, we're at the end of the 2nd month, I believe now, that we've been working on it. So we divided the project into 4 milestones. We are currently in between, I'd say, the 3rd and 4th milestone. Yeah. So we're still prototyping a few things, especially the mechanics. And so this holder here essentially holds a plate where the photovoltaic cell is mounted on. And so there's 3 magnetic micro-manipulators that we were talking about before that are what used to connect the electrodes onto the cell.
And the cell would be here, right?
So the cell would be here. And so you have software that controls the rotation on the 2 axes. And they already have an acquisition device, which is where the the wires are connected with the micromanipulators. They get the readings, the voltage from the cells.
Trying to find something that would
Yes, it's a good substitute to Smurfs. So, so that's it. So another part of this is software running on Linux, which is actually which is what's used to program the movements of the device, so that it can sync with the acquisition device and record the measurements. So what I'm showing you right now is these brushless DC motors that are being rotated very slowly at a precision of 0.2 degrees. So basically there's 2,160 steps happening right now per rotation. If you notice any jerkiness, it's because of the way the code is written. Last video I said that it was the curve that was on. It's not. It's because it applies the current, there's a delay. Applies the current, there's a delay.
Okay.
So right now there's that's going to be changed. It's going to be using timer interrupts instead, so that every few milliseconds.
So now they,
So the way it's going to work, the layer of the software on top of this is going to be the directional layer. So you're going to have an acceleration curve, depending on the distance, the angle that you want to move to. So you have an acceleration curve, it decelerates, and that's the layer that's on top of that. So the only problem we're having right now is we thought that this bigger motor here would have enough torque. Yeah. So this motor is supposed to be able to handle a weight of a balanced weight of 5 pounds. But right now, what we're experiencing is what was the calculations? How much weight on the?
well, it's a lever of 10 centimeters, and it's a lever of 10 centimeters. That's the distance between the axis of the motor and the center of gravity of the weight, 10 centimeters, and it should hold 550 grams. Just to be safe, 500 grams. At least it's a half a kilo on a lever of 10 centimeters.
Equates to about how much if it was a balanced
Well,
weight?
yeah, I can calculate the torque. We have a calculator that can calculate 500 something Newton meter.
Okay. There's still a couple of things to try because right now I don't have the full voltage of the amount that these motors can handle, and I have resistors going into the circuit. Because I don't have the MOSFETs on a heatsink.
So where's the chip?
So if these MOSFETs were mounted on a heatsink, I'd be able to drive them more. So it's not operating at the optimum. So this motor seems to be fine. Of course, this motor could replace this one for insurance. Yeah. But the solution to this problem would just be to get a bigger motor.
Yeah.
Because what we're trying to do is we don't want we eliminated the need for a gearing system, use any play or
Yeah.
or
So
use
essentially,
time. Yeah.
in 2 words, if you can just stop it, stop the motor rotation.
Yeah.
Wow, the motor got a little hot.
Yeah, it gets hot. So
Yeah. So this is the sun.
all the motors get hot.
Yeah. This is the sun. I know it's okay. I'll hold it.
Okay.
And there's a panel here that is a photovoltaic cell. And what scientists need to do to design this photovoltaic cell is how the energy, electrical energy that is produced by the photovoltaic cell changes the angle at any orientation possible. So this serves the purpose of creating all the possible orientations of the sample with respect to the sun. So
Because the light source is stable.
yes,
So the light source is stable in the lab, and so it's creating all of the different angles of incidence of the light.
exactly. So usually what happens is that the photovoltaic panel is on the ground and the sun moves around. Well, actually, it's even more complicated than that. It's the Earth rotating around the sun. That, it's as if the sun is rotating around the Earth. This is what we see from our perspective. Essentially, what we need to know for photovoltaic panels is how do they react to different angles of incidence of light coming through them. And we call that the quantum efficiency. So how effective is a photovoltaic cell to transfer light into electrical energy at different angles. And this two axis of rotation gimbal allows it to simulate any position of the sun in any part of the globe, okay, where a photovoltaic cell can be installed. So basically, that's what it is, and they just need to profile them. So they change the angles of orientation, and they measure the amount of current that that thing spits out. So then that information is used to improve them or to see if there's bugs. And some photovoltaic cells are very, very sensitive to the angle of incidence. And if you know that, what you do, you motorize them. You put the photovoltaic cell, instead of just gluing it on the roof of the house, you allow it to move towards the sun like a sunflower, follow the sun essentially, in order to utilize the maximum of its efficiency.
So is what you're saying that something like this could be used as a an on the ground instrument? This one's built for a lab to be able to test the incidence of light.
Well, there are
Perhaps a further use of it would be to actually orient PV cells out there. Is that what you're saying?
Well, that would be a huge.
Yeah, that already exists. I mean, you do have support structures for solar panels on homes that do a slight tilt to follow the sun.
Which
But
makes
this
sense.
material that he's testing is completely different. Eh? Can we explain that?
Yeah, it's a new type of
It's a new
photovoltaic cell.
Yeah, and actually the rotation of it plays a role too in its quantum efficiency.
Yes.
So
Yeah. So for now, it's just a scientific instrument.
yeah.
It allows people that design photovoltaic cells in the lab to model the sun and measure their quantum efficiency. So it's something that would be used in a university, or if some people, fab labs, want to get into photovoltaic cell, they can.
Can I see you guys? Yeah, thanks, Jim.
So the idea here is that this little instrument here is completely open source. And because it's mostly 3D printed, the cost is maybe 10 to 20% lower than commercially available devices that do the same.
Can you talk a little bit about open source, Tibby?
Well, open source means that the source are available.
So the data, the information on how something is built.
The recipe.
Exactly.
The recipe is open.
The 3D files, the electronics, so anybody can see how it works, understand how it works, build it themselves, or remix it with something else, change it, fork it. Okay. And the cost drops when you have it mostly 3D printable. So anybody at any university can build one for themselves. Or even if they order one from Sensorica, it will still beat the market. It will still be 20% of the cost compared to what's available on the market. According to someone we know, they said the prices are criminal.
Yeah.
So we're essentially building something.
Wait, you said, sorry, Tammy, you said it's 20% less than the market value?
It's
20%
20% of the market value.
of the market value, which is a lot more.
Because much of what people
Yes.
much of what people are paying for is the intellectual property, and so that is held by companies, right? And so what's different about the open source movement is that the way that you build something is open, and so paying that money for that intellectual property is not a part of the picture. Is that what you're saying?
This is accurate. Having intellectual property, you monopolize the market, yes, for a certain period of time, and you can extract more value, higher prices, right? Because nobody can operate in the same market. So you don't have limited competition. You control that little portion of the market. But there's also an economic impact on price, which is that if you design and produce this in a traditional way, okay, the way the system is set up is that you have to create debt as a startup to hire people, to rent the space, to buy the equipment, and you're starting from scratch because you want it to be proprietary. So you're doing all the work from A to Z in-house, and there's costs associated. Now, either you go to the bank and end up paying interest, or you go to an angel, which is venture capital, that will ask for maybe 10, 20, 40% of your company. And once the product is out there, you either have debt or you have equity towards these angels that come to help you go to market, meaning that debt or equity for angels will ask for a large cut of the profit. And now you have to supply the machine that enabled you to bring the product to market. So that is built into the cost. Okay? So cost of innovation is higher because you do everything from scratch, proprietary. Okay? And then you have debt accumulated or equity that you have to give away. Okay? Part of how the business takes off. Okay? And that forces you to operate at a certain margin. If you go 10% or 20% below, the bank is going to knock on your door, or your angel is going to knock on your door because they want the money.
You know what's really funny? I'll tie into something else about that. Outside of our collaborative environment.
Just to finish this idea, sorry, Jim. So now, once you do it open source, you don't care about proprietary stuff. So what you do integration mostly, meaning that you go out there and see what other people are doing. You just take the designs, copy them, and just add a little thing on top because you don't care to be original because you don't claim intellectual property.
That's what I was going to get to.
So you do a lot of integration.
What's funny is that outside of our circles, people tend to look at open source hardware. They think that they're free. Open source hardware means that it's free, meaning that it doesn't cost anything.
Yes.
But the free actually means that it's free to become. It's free to be modified. It's free to become whatever it asks it needs to become. The design is free to be turned into something else. I mean, essentially, what we did this for the R&D was capture everything that relates to this and choose the best solution for each subsection. But it's just a remix of other technology that's out there already. It's other open source hardware.
Software, hardware,
everything.
kind of designs. Everything. Yeah. But there is work involved, and there is materials that have to be printed in a lab. And this is a 3D printer that is used by someone, so yes, there are costs because all these people need to eat. And these materials that we buy, they require money. So it's not free as in free beer. It
can't be. No.
Well, and that's one of the challenges that faces the open source community is how to get funded and how to get resource to be able to take products to market. And so I think that it is good for us to talk about that because there's so much less that has to be paid for intellectual property because we're reutilizing knowledge that exists and processes that exist. But we do also need that some traditional funding to be able to make it work. So I just wanted to sort of put that on the table as part of the elements of what it is that we're dealing with when we're dealing with open source. Part of that is showing people the value of what it is to have actual models of the commons, which is what I see Sensorica as. It's a model for the commons. And I think it's a very valuable way to be able to bring products to market and have people work together as collaborators and be able to make those agreements about who earns what and how. So I really appreciate you guys banging out the model and that we're working so hard to make it understandable for people as well.
Well, it beats working in a company, that's for sure.
Yeah, it's more fun.
It's more fun. You enjoy the path more, especially when you're collaborating. It's a whole different feeling. You're working on a project, and I don't know. There's some kind of euphoric feeling when you're collaborating with somebody on the other side of the world. I think. Actually, we had a good article about that. Remember that article? What was it? They were comparing collaboration to sex.
Yeah, there's something erotic about
online collaboration.
Online collaboration.
Swarming the project and having people.
Yeah. I think it's the feeling of other people showing interest in what you're doing and adding on top of that, and it's just like It's such an innovative environment. It's a different feeling, I guess.
Yeah, it's very powerful what happens when we think together because no one person has the answer. And I think that part of what we're learning through these projects and through the Sensorica project more broadly is how do we think together? How can we collaborate in a way that allows each person to bring their piece to the table to make the whole stronger?
Okay, so should we should we wrap this up, Tammy? So about the needs for crowdsourcing now for this project. I think so. We had a few weeks of
Downtime.
for this particular project,
Yeah.
which is very, very important for us because it is a paid project, and so there is income generated. So it's very, very important. As important as going out there and look for alternative funding. So I think one of the actions here is to revamp the momentum. Okay, bring up momentum within the group. That's in the forum, right? By making it very clear, concrete. This is what we have to do now. I think once we receive the second check, that's an incentive.
Another incentive.
Okay, because,
Well, of course.
because the promise was fulfilled and some people will get paid. So talk about that.
Yeah, there's a couple of people getting a piece of the pizza.
Yes,
All over the world.
Yeah.
Piece of the pie.
Yeah, so maybe we can coordinate this. The check will come within this week, maybe, hopefully, and then we can share that information, share the check, and then bring back momentum within the network, and then go outside and bring more resources because I think there's got to be some redundancy here.
Yeah, for sure.
In electronics and software, in mechanics, we kind of have a good grasp of what we need in mechanics. But electronics, I still don't know what it takes to
Look,
finish this.
electronics we said for this system is very simple. Don't look at what this looks. It's like a jumble of wires. It looks complex.
What about the UI then?
This is sorry.
UI.
That's where we're at with the software now. The core is pretty much complete. There's just a little retweaking to do. There's the other layers which Thomas and Ahmed were working on. I wanted to take charge of the UI, but like we said, the downtime kind of affected us last week. So that's where I'm at, and Maria wants to work on that today.
Oh, nice.
Yeah.
That's why she wanted to be with us on the Hangout.
Yeah.
That's cool.
It's too bad she couldn't join us.
Yeah.
Well, I don't know. I just sent her an email. And she probably thought we're going to be ready at 11:30, but yeah, it took us a little time. Well, Tammy, should we wrap this up? Or?
Yeah.
Okay. So thanks for your collaboration. We also have the Reading Game project, which is advancing very, very nicely. So we would like to 3D print the casing today. Jim went to buy some parts, so we want to jump to
I didn't
that.
buy them. They were donated.
They were donated by a store, so when you are an open project, people donate to you because we're doing such a great work. So yeah, if you want to be part of that one too, I think Valentine is here and
Fabio's here.
Fabio's here, so we're going to talk about outreach as well for this project. Are you interested, Tammy, or?
Sure, when is it happening?
Maybe just a little break.
Yeah, we have to go.
Yeah,
These guys gotta
after lunch, yeah.
Okay.
Is that okay with you?
Yes, I've got a commitment at 4:30.
Okay.
I need a little bit of time to prepare, so
Okay.
great.
Yeah, no problem. So we're gonna go to lunch and then we. Oh, look at that design. This is really cool. Okay. The box. Okay, Tammy.
All right.
Thank you. And let's hope people come back from vacation. It's already September, so we can accelerate this. Yeah.
Great.
Okay.
Bye.
Bye bye.